Hi, I'm Paddy Delaney from Huber, and today I'd like to talk about the topic of flow and pressure. As we discussed in our previous webinar and white papers, critical to optimum temperature control is efficient flow through your system. You want high flow rates with a low enough pressure. Of course, we appreciate your application may have some back pressure, so we do have to apply a wee bit of pressure to get the fluid moving in the system. A quick overview of what we're going to talk about today. When you've got your temperature control system, a lot of people are fearful of putting them on glass reactors because a lot of manufacturers say they're rated to half a bar pressure, and that's right. However, a lot of people do not take into account positioning of adapters, valves, manifolds in relation to their application and the pressure drop they see from their TCU system all the way to their application. And I'd like to just show people using some experimental data and some practical data what we mean about flow and pressure and what is the true value seen by your application. So if we take a step back, if we think about flow and pressure, they are related. If we draw a simple graph of pressure versus flow, we've got pressure here versus flow, and we say liters per minute, and let's go good old bar here. So obviously the higher the pressure, the lower the flow rate. So you'll see a common factor in a lot of Huber units is we go for low pressure pumps with regards to high flow rates so that we get efficient cycling of the thermal fluid in the system. However, some of our pumps are rated to greater than half a bar. What do we mean by that? So if you go on the Huber website and you actually look at a product, if you click on the right hand side below the image, on most units you'll find the pump curves. But there is always a value which is greater than half a bar. And people go, well, your pump says 1 bar, 0.9 bar, whatever. How is that measured? That is actually a deadhead pump value. That's where we put an inline valve and we shut it. That's the maximum pressure you will generate. And at that point, you have zero flow. It's something to be aware of. Some people misconstrue their technical data sheets, so it's a bit harder to tell. But at Huber, we're open and honest about this sort of stuff. And we're quite happy to supply our pump curves. Another way of looking at the pressure-flow relationship, kind of a more simplistic way, is if you take a tap, forgive my drawings here, if you have a standard tap without any restrictions here, you get high flow rates. But low pressure. If we take the same tap and put like a garden sprinkler hose on it, so in this case we'll draw a hose very badly with one of those daisy style heads, like a shower head on it, where the water is going that way. We get a medium flow rate, but because we've got a bit of back pressure, so this is a restriction, we run a medium pressure here. And if you think about the other style of garden hose, which is more of a straight through, so again we draw our hose. And this is more of a cone-shaped hose, a bit like a power hose or something like that. You get more directed flow from that. So this will be a low flow rate system. So we've got low flow rate, high pressure. If you think about it, it's a bit like what they advise people to have a shower rather than a bath, because a shower head uses a lot less water, but it generates a more forceful water for cleaning you. So this is kind of a key principle here. And at Huber, we'd like to stick down this end because this gives you the best flow rates through the system and therefore thermal transfer. But how do I relate this to my reactor system? So we'll do a basic graph here and then we'll start talking about some individual units. So if I put my TCU here and my reactor body, and obviously we've got our fluid in at the bottom and back out at the top for optimal temperature control. We have our agitator. Like I said, most reactor manufacturers rate their units to 0.5 bar pressure applied. If our TCU has pressure X, this pressure may be measured internal on the unit or it may be on an external pressure sensor. But we'll go through that in a wee bit more details in a bit. And we have our application. So the pump has pressure X, is entering a large cavity here. So our pressure at the inlet is approximately equal to pressure X. But if we apply half a bar here, it's not going to break our glassware. What we need to look at is on the exit, so we're applying the pressure across the whole vessel, not just on the inlet. That way your system is seeing the full pressure applied. So where you need to look for is on your exit. So on your exit, because you're pumping from a smaller ID tube here into a larger ID volume here, and then back out again, you do get a pressure drop. So on exit, it'll be pressure X minus pressure drop Y and this is the value you've got to be careful of. So when we look at our different units that are available, at Huber we have our open bath systems like our mini stats, our CC 405 all the way up to our CC 902, and then we move to our Unistat family. They all have different ways of working the systems. If we look at our open bath systems like our mini stat, they're open bath, so they're not a sealed system. In these units we do not have an inbuilt pressure sensor. However, we can adjust the pump speed. By adjusting the pump speed we can reduce the pressure being applied on the reactor system. However, as it's open bath, any expansion in oil or additional pressure is kind of the effect is seen on the bath. So on the open bath systems, we do have a little quick guide on how to adjust the pump speed, and that'll be shown on the opposite side now. So we've just gone through the relationship between pressure and flow and how on a reactor system you'll see a pressure drop across the reactor. So using our chili, how are we actually going to measure what we're planning on doing? And what we're planning on doing is a couple of experiments measuring the pressure on the inlet and the pressure on the exit in a variety of scenarios, i.e. pump speeds and stuff like that. The first thing we're going to need is E-grade Explore, which is an optional E-grade on all Unistats, where you can see your TI internal, your TR return, and your TE, your process temperatures, and the delta T's between them. In addition to that, it allows you to log the pump pressure sensor, be it on the pump outlet in the system you have already, or you can use an external pressure sensor and place it. In our case, we're placing one on the inlet and one on the outlet, but only taking one signal off it. In addition to this, via our 420 milliamp signal, we can set up a flow meter. Because we're using the SIL oil and because of our temperature range, I've chosen one of our turbine flow meters here. You can actually get ultrasonic flow meters as well, but for the little baby systems, I find the turbines are just perfectly fine. What does that all mean? So if we go into the menu and our system settings, in normal mode, you can see, if you click on pump, you'll see pump control mode is either speed or pressure on a Unistat. If we go pressure, we can adjust the speed by clicking on it and entering a value between 500 and 3,500. And the unit will then operate at that speed. If we go back and we actually pick pump control mode pressure, we can actually select half a bar, say for a glass reactor, as our pressure setting, and the pump won't go above half a bar. It'll modulate its RPM or speed to hit that value. However, as the whole point of this webinar, that is the pump pressure at the pump outlet inside the machine. It's not at the inlet of the application or the outlet of the application. So we've got to do a few more things before we're ready to do our experiments. First thing we're going to do is set up our flow meter, our inline flow meter, and our pressure sensor externally to the unit. This is done via a Huber comms gate, and in this case, because I want to tidy up the wiring on the system, I'm going to use our CAN gate, which is an extension of a CAN bus system. It allows us to connect multiple flow control accessories at once. So let's go into the menu and we go interfaces, and we go for this little iPod looking icon down here. This is the AIF, or the analog interface. We're allowed to put one input in and have 3 outputs. So on the input, we're going to select our flow meter. We go down the menu, near the bottom we've got thermal fluid flow. If we click on this, we then get the option of what are we going to set as our 0 milliamps, or what we're going to set at our 24 milliamps. In this case, the chili is got a flow rate of 0 to 45 liters per minute. So 0 liters per minute will be our 0 milliamps. 45 liters per minute will be our 24 milliamps. We're done now. We can go back out and we go to our outputs menu. We've got 3 options here. 2 of them are fixed at internal temperature and process temperature, but on the bottom channel 3 we can adjust it. Again, it's near the bottom, but we can go pump pressure setting. So again, case with our chili is set up for 0.9 bar pump. So at 0 milliamps we have 0 bar. At 24 milliamps we're going to set it at 0.9 bar, and that works within our operational range. Now if we go back out to our pump menu, so if we go menu, system settings, pump, you can see we've added 2 more functions here. We've now got flow control function, because we can use our external flow meter rather than just doing pump speed, so we get actual flow rates. So now, instead of just having speed and pressure control, we now have flow control and flow control pressure limited. So if we are worried about a sensitive application, in these cases we're putting in, we would like to deliver X liters a minute, and that works away. And in the case of flow control with pressure limit, in pump control mode, you can, in pump control pressure, you can set half a bar if you're worried about it, and the unit will only operate up to half a bar. If your flow rate is in that range, it'll hit it. If your flow rate is outside of that range, it will only operate to half a bar. It won't push it any further than that. So this is quite valuable, that we can do this with a simple setup like this, or Huber do have another setup where you can go from 0 liters a minute. On a small system like this with a variable pressure control pump, you're limited to whatever 500 RPM is as a flow rate on your application. Whereas if we go with the fully automated variable pressure control system that's external to your unit, we can go all the way from 0 liters a minute to your maximum achievable flow rate. Again, we could hook it up something like this, But Huber also have our flow control cube, which is an all-in-one package where we've got our VPC, we've got our pressure sensors, and we have our, in most cases, they have inductive flow meters. And they're very useful for a lot of automotive testing sort of applications. It's a plug and play setup. So now we have our experiment designed. We have all of our settings ready. We've got our manifold on the back of our chili. We've got our pressure sensors in position P1 and P2. We're going to work with our 3 fixed flow rates of 1500, 2500, 3500 RPM. And we're going to look at the effect of pressure readings, the pressure at each point on the reaction system. In our Unistat family of products, we do have an inbuilt pressure sensor as well as our pump. However, in certain Unistats, we have fixed speed pumps, whereas other Unistats, we have what we call a VPC pump, which is a variable pressure control pump. Utilizing this pump, we can actually go down to 500 RPM up to 3500 RPM and adjust our speed with relation to pressure. So when you do slow it down, you get a reduction in pump speed, or you get a reduction in pressure. However, you cannot go to absolute zero. Some applications require absolute zero. We'll bring them up in a minute when we talk about an externally mounted VPC. So looking at our Unistats, what I've decided to do today was bring our chili in. It's our smallest Unistat. It has a 0.9 bar pump and it operates at 0 to 45 liters per minute flow rate. So to test the principle of pressure on a reaction system and where we actually see our pressure drop on the system, we've hooked up our chili to our Radley's reactor system. We've fitted a bypass manifold onto the back of the chili. So we can see if we bypass some of the fluid, will that have a dramatic effect on the pressure seen by the application? What do I mean by that? Well, if we think of our application again, we'll do another quick sketch. If we go on our TCU, and we've got our application here. Inlet and outlet. So to reduce the pressure on this, there's one option where if we draw this like this, and we go do the return line, going back to the unit, can we actually have any effect by fitting a bypass here? So instead of all the fluid being seen by the application, a proportion of it is bypassed and it's fired back up around to the TCU. We have two options here. We can either use a manual bypass, which looks like this, but I have de-armor flexed it. So we have essentially a ball valve capable of working at temperatures and HTF compliant, and we can open and close it to whatever opening we want, and we hopefully will see an adjustment in the pressure seen by the application. The other option is a fully automated system led by Huber, which is what we call a mounted VPC bypass. In these systems we can connect a pressure gauge and we have a fluid flowing through the system, background, and you can get bypassed here from the application. You will have seen this in the white paper, and we'll bring those graphics up again just as a reminder. So the test we're actually going to do on this system is if we put a, we'll call it P1 here on the outlet, P2 on the inlet. If we apply a certain pump speed and pressure on each one, and what we decided to do is adjust the pump speed to 1500 RPM, 2500 RPM, and 3500 RPM, kind of full bore. What effect will we have on the pressure seen on the inlet and the pressure on the outlet. Versus outlet. And then we're going to do this in two cases. Manifold, bypass manifold, open and closed, to see, can we get a fine balance to know the ideal setup of, do we need a bypass manifold? Can we adjust the pump speed? Will that give us enough of a difference on the inlet and outlet? And like I said, we've done all of this work on the chili with a Radley's 1 litre reactor. And what you will notice from our testing is that when you're running at 3,500 RPM, because of the size of the 1 litre reactor, we don't see much of a pressure drop across the application because we're forcing the fluid through at a good speed. When you go to lower RPMs, the difference between P2 and P1 is far more dramatic. And again, you'll notice if we use a manual bypass, we see the largest drop is converse on this. The largest drop is on the 3,500 RPM versus the 1,500 RPM. So it's a bit of a fine balance to get your ideal setup, but we can easily measure there is a pressure drop across your glass reactor, and the best way of showing that is putting pressure sensors as a test. If we correlate that back to the pressure sensor in the TCU, this will still be showing. So if we take, for example, this is showing 0.9 bar, our P2 would be showing 0.7 bar, and our PI would be showing 0.5 bar, due to the associated pressure drops. In our case with our chili, the main reason for our pressure drop on our inlet is the fact we've got an inline flow meter, which is disturbing the flow and causing a pressure drop. Then we have, like I said, we have our drop across the jacket and then back to the TCU. So we've been and we've collected our data from each setting where we've run the pump at 1,500 RPM, 2,500 RPM and 3,500 RPM. We've taken our pressure readings from the machine, the inlet and the outlet, and we've also done with bypass open and bypass closed. So this is a hell of a lot of information. So we're just going to show a quick clip of it stabilizing, and we're going to go into some data that I've graphed up to make it a bit easier to understand. In the first graph here, we're looking at a pump speed of 1,500 RPM. Now, if we look at the graph, we've got two columns for each section here. We've got a blue column, which is our bypass open, which will, in theory, relieve a bit of the flow pressure on the application. And we've got our grey column, which is our bypass closed. At such a low RPM pump speed, what we can observe is that when we have our bypass closed, the pressure reading at our unit outlet, application inlet, application outlet is all roughly the same, about 0.19 of a bar. However, if we do open our manual bypass to relieve a bit of the flow and pressure being seen by the application, we can then see that our pump outlet pressure drops a wee bit to just below 0.18, and our pre and post application just dropped below 0.17. So we're seeing a 0.02 bar of drop. This isn't a large drop, but this is mainly down to the fact we're running at a low pump speed. So if we increase our pump speed to 2,500 RPM, we see a little bit more of a difference. So let's start with the grey columns. This is our bypass closed. Our pump outlet is just below half a bar. The entrance to the vessel, which is seeing a little bit of a pressure drop, is just above 0.45. And our exit of our application, again, is at 0.4 bar, just slightly above it. So we can see that there is a pressure drop observed from our unit to the inlet and to the outlet. When we open our bypass again, obviously on the pump outlet, it drops the most. When we look at our inlet to our application, we get a little bit of a pressure drop from just above 0.45 bar to just below 0.45 bar. And interestingly, we see post-application, we don't see much of a difference. So this is telling me we've roughly balanced our pressure drops across our application on the system when we're running at 2,500 RPM. We can see that we're running at 0.4 bar on the reactor outlet, which is a nice outlet pressure to give enough of a feedback pressure to return thermal fluid to the unit. Our next speed we look at is 3,500 RPM, where again we're running faster, so we're applying a wee bit more pressure to the system. Again, looking at the grey bars here, we now see that our pump outlet is almost at 0.9 of a bar. Our inlet to application is just above 0.8 of a bar, and our outlet from the application is just below 0.8 of a bar. So we can see again, we're still seeing a pressure drop across our piping system from start to finish. This time, however, we see a bit more of effect on our manifold being open or closed. So when it's on the pump outlet, because we're running at such a high RPM, the fluid is actually being pushed through the system. So if we open that outlet, we're just seeing roughly a 0.25 bar of a drop. The same can be said for pre-application, and the same trend again at post-application. So we've now looked at all of our data from 1,500 to 3,500 RPM with our different scenarios. If you remember back to the start of this webinar, I mentioned how we've got to look at pressure across an application. It's not really the pressure on the machine or on the inlet, it's on the outlet of your application that is key. So what we've done now is we've graphed our 1,500 RPM, our 2,500 RPM, and our 3,500 RPM onto one graph based on our pressure reading post application. And we've done this for both open and closed manifolds. Obviously we can see that when we increase our pump speed, we're applying a greater pressure to the system because the pump is forcing fluid against a kind of a back pressure restriction. So if I was setting up my glass reactor, just looking at this graph, I would probably choose 2,500 RPM pump speed, and the fact that we don't really need a manual bypass because the results for open and close are pretty much bang on the same. However, we do try to get optimum fluid transfer to optimize our temperature control. So in most cases, you're better off running the pump at full speed. So to run the pump at full speed on this application here that we've tested, if we had it closed, we'd be just running at 0.8 bar. However, we could throttle back the pressure being observed by the system by adding a manual bypass. And when we open that, it's just slightly above 0.5 bar. So we've looked at various concepts here, and we've shown that we've actually run systems with a pump pressure greater than half a bar on glassware, where manufacturers say you shouldn't exceed half a bar. But the key fact here is none of our systems are truly sealed systems. If we were to run what I'd call an externally open machine, which is a bit like a hydraulic line on a tractor, the fluid cannot expand. There's no room for expansion in the system. So when you apply a pressure, say a piston moving against it, it would break. So if we had a truly sealed system and we're either A, warming up from a cold temperature, or B, heating up from room temperature, the oil would expand and would apply a hydraulic pressure onto the glass and would cause it to break. So to prove this a little bit further, we're going to look at two more things. We're going to look at number one, booster pumps, and number two, what is the true hydraulic pressure on a glass reactor and how it will actually break. So we've looked at pressure drops to the application and across the application. But what does that mean in the real world when it comes to delivering thermal fluid from a reactor to and from the TCU? So if we have our TCU And it's quite a common problem where it's in a plant room, outside, up on the roof, somewhere not adjacent to the fume cupboard or the application. So again, we sketch our little reactors and try to feed to the bottom and then out the top. We might have vertical height to climb, something like that, to get the system, get the fluid all the way across. Sometimes it's easy enough to get your fluid to the application where we've got X pressure feed. So the feed equals X pressure. Obviously we talked about our pressure drop. And then our return equals Y pressure, and that should equal X pressure minus pressure drop. We should still have enough pressure to get us there. However, this isn't always the case. So in this scenario, Hoover does have a range of booster pumps that we can put in line. Sometimes we need them on the feed line because the application may have a high back pressure, say like a flow reactor or a plate or a cold plate or something of that variety. But when it comes to glass reactors, glass line stainless steel reactors, normally if we need a booster pump, they're put on the return line. So here we've set up the booster pump on our chili, where we've just done a simple setup where we've got on the outlet of the system, we've got a flow meter going into our booster pump, and we've got our pressure gauge at the back, all feeding back into our E-grade Explorer. What we'll see here is we're going to turn the system on without our booster pump running. So when we turn on our chili, we can get it running. We can see we've got nice stable pressure and we've got a nice flow rate. It's not fluctuating much. So let's turn on our booster pump and see what happens. Now we're going to have to give it a minute because we've got two pumps in the system here. And what you'll find when you initially start up pumps is it's kind of the opposite to trap air. You get cavitation because you've got a push and a pull system. So the pump on the unit is pushing, whereas the pump in the chili is, and the booster pump is pulling the fluid in the feed line. So what we might find for the initial few minutes is we get a cavitation. So you'll see the pressure dropping and going back up. But what we can see from running the booster system is when we turn the booster pump on, we get a reduction in flow rates, because as before with our diagram, as pressure goes up, flow goes down. So the higher the pressure, the lower the flow. A side effect of booster pumps, which we can't avoid, is a booster pump will add heat to your system. So on our chili, we've actually turned off the heater on our units, so we're not applying any external heat via the heater cell. So what you'll notice is there's been a temperature increase on the internal fluid temperature and the return temperature since we turned on our booster pump, because obviously it's agitating the fluid, and in this case it's a direct drive pump. We do have some magnetically coupled pumps, but then again they will also add in heat to the system. So if you're getting a booster pump for your system, bear in mind you've got to take that into account if you're applying cooling to a system, because that heat will knock out a proportion of your cooling. It's only between 300 and 600 watts, but it's something to bear in mind. Obviously, if you're in a heating TCU like a chili, it's not going to affect it much because it's adding extra heat. It's adding to the function of the unit. So in this webinar, we've talked a lot about pump pressures, pressure drops, even booster pumps, bits like that. But every so often we get a phone call, my reactor's broken. How's that happened? or we've smashed a glass application, or we've cracked it. How's that happened? Well, we've seen from our work we've done earlier in this, we can run systems above half a bar and they're fine, because most of the Huber units are open. Don't get me wrong, we do have closed loop systems called EO versions, and if you were to put one of them on a glass reactor, it would probably break. But why is that? It's down to the hydraulic stress and hydraulic pressure being applied by expanding thermal fluid. It's nothing to do with the pump pressure. So if we think about the Huber units, if we've got our reactor system, if we've got our, sorry, it's my usual standard beaker reactor with an agitator, we've got our inlet and our outlet, and we've got our TCU here. So we've got our TCU. If you look at the Huber case studies, and if you wanted one for the Huber chili, you'll notice we've got a little small unit like this, heating a glass reactor, 20-litre glass reactor to nearly 200 degrees. And if you quickly think about how much that thermal fluid's expanded, it's actually expanded by about 2 litres. It's about 12% per every 100 degrees. And where does that 2 litres of fluid go? Because this is the hydraulic pressure I'm talking about. So if we look at our TCU and we were to go 0 to 100 degrees C, and say we had, let's just say a nominal value, we've got 10 litres of fluid in the loop. By going from 0 to 100, we end up with, it'll be 11.2 litres of fluid in the loop. If that was a true closed system, that would apply a pressure on the glassware. However, upon heating, we've got two options in a Huber unit. In an open bath system, it literally goes into the open bath and expands. However, in our Unistat system, normally in the top left-hand corner, we have what we call our expansion tank. And we normally run these at about 30% fill volume. The reason for that is our extra 1.2 litres in this system will actually push its way into the expansion tank. Which is open to the atmosphere and thermally inert. We can get a sealing kit for a nitrogen blanket, stuff like that, if you need it. But the extra fluid volume is actually being pushed up into the expansion tank, not onto the glass walls. If we didn't have our expansion tank set up on our Huber units, or our open bath systems weren't truly open, that volume of fluid would be sealed inside the jacket and would be applying a pressure to the jacket, and that would cause your jacket to rupture. So we can see by having an expansion tank inside of our Huber units or using an open bath system, we can heat up and cool down and heat up to room temperature and not exert the pressure generated by that fluid expansion, the thermal fluid expansion. But how do we actually prove this? We've got hundreds of case studies showing thermal fluid expanding in Huber units with no issues. But I wanted to actually prove how does a reactor actually break. So what we've done is we've commissioned a bespoke jacketed glass cylinder. It's got a 6 litre jacket on it. We've put shut-off valves on the inlet and outlet. We're going to use a Ministat 230 on this one, and we're going to use our M20 sill oil. You could use any sill oil for this. They'll all expand when they start heating up. And what we've done is we've actually chilled it down to -14, so that we've got a nice starting temperature. We don't have to go crazy. I don't have to go -80. I reckon if I go from -14 to 0 degrees C, that'll be enough to cause issues with our reactor system. So if we think about the temperature range that we're actually going to work over, how much will our thermal fluid expand going from -14 to 0 degrees C. So in our reactor sizing webinar, we went through our calculation of expansion of thermal fluid. It's a quite simple formula, and I've simplified it even more here. So it's essentially the delta T. We're going from -14 to 0. We've got a volume of 6 litres, and the density of this seal oil is about 0.95. So what this means is, going from -14 to 0, our seal oil will expand from 6 litres to 6.09 litres. So we're not even seeing 100 mil expansion in our thermal fluid here. So bear that in mind. We then have to look at, would warming the glass from -14 to 0 apply a stress to the glass? So this is where life gets a little bit more complicated. And we calculate the stress that was applied on the glass due to the increase in temperature. This is a bit more of a long-winded equation, because you can actually work out the force on a restricted pipe. We call that F. That equals sigma times the delta T times the surface area. So sigma delta T is kind of a pressure calculation. And if we do in the maths from my P&ID drawing of my glassware, it works out at 282 megapascals. If we then look at the surface area of the tube, we're looking at about 4 by 10 to the -3 meters squared. So it's quite a big old tube inside and out. Now, when we combine both of those parts of the equation, look at our F equals sigma delta TA, it's handy enough, and you actually get the force applied to the glassware based on that temperature increase is about 1.1 newtons. Okay, what's a newton? Newton is essentially mass by acceleration. If we sit this pen on the table here, say the pen weighs 20 grams, the acceleration is 9.81 meters per second squared, gravity basically. So let's work back our newtons to work out what is the weight of an object sitting on another object. So it's quite simple. It's our Newton value equals X kilograms times gravity, and we can work out that the weight of the item being applied to the glass is about 115 grams. So really, it's like putting a large apple on top of our glass reactor. That's the kind of stress being applied by the temperature increase. So that tells me that I'm not working over enough of a temperature range to shock the glass. If I was working over maybe an 800 or 900 degree delta T, we might be in the range of applying stress to the glass that would cause it to rupture. But bear in mind, they do anneal glass in ovens, you know, so it does take a fair whack of a delta T. So where are we on this? So we've looked at the expansion of our fluid. We've looked at the stress being applied by the temperature difference. The question now is, what stress is actually being generated in the sealed tube? So bear in mind, we've run the system down to -14. We're going to let it warm up to 0 degrees C. And we're going to lock. We've got shut-off valves on the inlet and outlet. So let's look at the fluid inside that jacket. If we look at the bulk modulus for our polydimethyl siloxane oils, it ranges quite a bit. So I've gone with the worst case scenario, and a lot of people give that as about 360 millipascals. If you think of a Pascal, we're looking at 1 bar, so we're looking at about 360 bar. So in that, we need to do 360 bar times our delta V, so that's our increase in oil volume, over the original oil volume. And what you'll find is, by just increasing by 90 milliliters in a sealed tube, the hydraulic pressure we're applying to that glassware is about 5.4 bar. So that tells me, do not lock thermal fluids into your jackets. And the majority of cases where people have broken reactors, from my experience in designing reactor glassware and working for Huber and actually working in Kilo Labs, is where someone's had quick disconnects on their glassware, or they've had shut-off valves with no pressure relief systems, and they've locked in the fluid, and they've either, I've seen one case where one customer locked it in and they moved it to a window, a bay near a window, and the heat from the sunlight was enough to cause the oil to expand to cause a rupture. Another one I've seen is moving from a cold storeroom, which is kind of like a shed on a chemical site, where it was 5 degrees, and they brought it into an air-conditioned lab at 18 degrees with the fluid locked, and that was enough to get it to break. Key message here is, please don't lock thermal fluid in your jackets. It's not the TCU that's breaking your glassware, it's physics. It's the expansion of the thermal fluid applying hydraulic pressure across the glassware. So what does that mean for our ill-fated glass tube? We're going to show a video. We timed it. It actually took 40 minutes to warm up from -14 to 0 degrees C. We've time-lapsed this a little bit, but we've also slow motioned the brakes on it as well to show the glass actually ruptures. We didn't have a live unit on this. We've isolated it from the unit with shut-off valves. There's nothing pumping. This is purely and simply oil expanding when it's getting warmer. Like I said, it only increased by 90 milliliters, but that 90 milliliters locked in this glass vessel was enough to apply 5.4 bar of hydraulic pressure. See? So as you can see, the glass doesn't survive hydraulic pressure being applied. The reason I've done this is just to prove that it's not a TCU that can apply it. If you've got the correct TCU that's either open batt or it's got a built-in passive expansion tank that will accept your increase and decrease of thermal fluid volumes, it's key to remember that. If you're really still concerned, fit pressure relief devices to your lines. We'll happily advise. If you want to do quick disconnects or shut off valves, we always recommend pressure relief devices. But what I will say is, if you do have any further questions, don't be afraid to speak to anybody within the Huber organization. We're all here to help, and we've all got experience of setting up complicated glass reactor systems. And I guess on one final note is, whenever you make a mess, you got to clean up your mess. So that's what I'm going to do now.